All right, so today we're going to get into some more story problems, but in particular mixture problems. These are definitely a little bit more real-life-esque, I suppose, than the last set. A lot of chemistry applications here, why you have to mix solutions and things like that. So let's just jump right into it. We still want to talk about the best method for solving, but to answer some real-world, real-life situation questions, right? So first thing here, Dice Dairy Farms produces low-fat milk. So they produce different types of milk. They produce 1% milk, which is 1% fat, and 3.5% milk, which is 3.5% fat. And they need to come up with 100 gallons of 2% fat milk. And this is the only two types of milk that they have, 1% or 3.5%. Or maybe they could come up with 2.5%, but they've got these two mixtures, 1%, 3.5%, and they want to combine those to come up with 2% milk, right? Without getting into how different fat content of milk is produced. But okay, so we always start the same way as we did the last ones. Underline the question, because that tells you how many variables and what you have to make them, how you have to define them, right? How many gallons of each type should be combined? So there's two types. We don't know the number of gallons of each one. So we can let X be the gallons of 1% milk, and Y can be the gallons of 3.5% milk. Okay? Well, we're going to mix them, right? So if we put those 2 gallons together, we want them to produce 100 gallons of milk. So if I add X and Y together, that should equal 100 gallons. Okay? So that's going to be your first equation when you do a mixture problem, is if I add the two amounts of the two different mixtures, that has to equal the amount I need of the final mixture. Okay? Now, the second equation is going to come from the percentages, the fat percent, right? How much fat is in each of those amounts? Well, to find out how much actual fat is in the 1% milk, I take the amount that we're going to use, which is X, and multiply it by its percentage. And I'm going to make it a 1. I know that typically we put percents into equations as decimals, but I'm going to use the percents for all three amounts, so that makes them all the same. I don't have to worry about making them decimals necessarily, okay? Except for the 3.5% milk, which is already a decimal, even in its percentage form. But that's the same deal, right? I got to take the amount I'm going to use of the 3.5% milk and multiply it by its fat percentage, so I know how much fat is in there. And I have to do it for the 100 gallons also, right? The 100 gallons has 2% fat in it, so I got to multiply the 100 gallons times 2. So a little bit different than those coin problems where we're multiplying the coins times their value and then just equaling it to a total amount of money at the end. The problem here is I don't know how much total fat there is in the 100 gallons. I've got to figure that out, and multiplying the 100 times its fat percent is how you figure that out. Okay? So there's my system, and I still want to go through and solve it. I'm going to use elimination by multiplying the first equation by -1. That will make my y's opposites. Okay? So those will add out to 0. I get 2.5y here. Now, I've got to multiply these two guys together and get 200. That way when I add 200, -100, I get 100. Right? And so now divide both sides by 2.5, and you get 40. So it tells us that we need to use 40 gallons of the 3.5% milk. Well, use some common sense, or plug 40 in for Y and realize that it's going to take 60 gallons of the 1% milk. So you need to, so you can say they need to use 60 gallons of the 1% milk and 40 gallons of the 3.5% milk. Okay? So that's a mixture problem when you're mixing two things together. This one you have to multiply the final amount times its percentage also, right? Because there's a percentage to multiply it by. A little bit different in some situations, and we'll talk about that. Okay, actually, now, this equation, or this story problem, gets us into how we don't multiply the final amount times its percentage or times something, right? So, we're going to mix some tea. One tea that's worth $1.25 a pound, and one tea that's worth 65 cents a pound. The question is, how many pounds of each kind do you have to use to mix, right? There's two different kinds, and so X and Y are going to stand for the pounds of $1.25 tea and pounds of 65-cent tea. Okay? So if I add those 2 pounds together, I want those two to add up to 150 pounds. That's how much that we want to end up with. Okay? Now, it's not that we were trying to multiply by the percentage of tea. It's all tea, right? But they are priced differently per pound. The $1.25 a pound, right? So now we're going to convert everything over, these amounts, over into the value, how much they're worth, right? Well, if I have X pounds of $1.25 a pound tea, to come up with its worth, I got to take the $1.25 and multiply it by the number of pounds. It's a price per pound. Same thing for the 65-cent tea. It's a price per pound. Now, in the mixture problem before, I would have taken the 150 and multiplied it by its price per pound, right? Because that's what I've done with every other amount. The problem is the $109.50 is not a price per pound. It's just a total price. So it's almost like I've already multiplied the 150 times something. So I just got to put 109.50 in here. This is going to be the most confusing part. And so we have to keep trying, keep talking about why we're either multiplying or not multiplying. Okay, but hopefully that makes sense. Since the $109.50 is not a price per pound, then we don't have to multiply that by the 150. Okay? Now, if they had said something like the price per pound of the new mixture is $1.10, then we have to multiply the 150 times $1.10. But they didn't say that. Okay? So, we got an equation here. Now, just like the coin problems before, we could make these not decimals by turning these all into pennies. Makes the numbers pretty big, but at least I don't have decimals anymore. And I would use elimination by multiplying this first equation by negative 65. That will allow us to eliminate the y's. Again, the numbers get big, but we also have calculators, so we're okay. So we get 60x equals 1200. So x ends up being 20, which means that we are going to use 20 pounds of the $1.25 tea. And again, common sense, or actually plugging this in, tells us that means that we're going to use 130 pounds of the 65-cent tea. Okay? And you want to write that into a sentence answer. Okay? So hopefully that makes sense. The difference makes sense. Try setting this one up. This is a mixture, so you are going to multiply that ending amount by a percentage. Okay, but stop the video, give it a shot. Writing is trying, and then start it back up and see if you're right. Okay, so how much of each alloy should be used to combine? So we're talking about kilograms, right? We want to end up with 4 kilograms of a new alloy. So we need to find out how many kilograms of 30% alloy needs to be mixed with how many kilograms of 10% alloy, right? Well, if I add those 2 kilograms together, they have to equal 4 kilograms total, right? Well, each alloy has its own percentage of gold. So each alloy we need to multiply by their percentage, the X, the Y, and the 4, because the 4 has its own percentage of 15. Okay, And then we solve by multiplying the top equation by negative 10, because that will make our y's opposite. This ends up being 60, so we get negative 600 here. Okay, so that's what, 20x equals negative, wait, sorry, back up. That was going to be a weird answer. 4 times 15 is 60. I'm multiplying the negative 10 times the 4, so we should get negative 40. So we're going to add those two together and get 20. Right, divide by 20. And so that tells us that we need to use 1 kilogram of the 30% alloy, and obviously we're going to end up needing to use 3 kilograms of the 10% alloy to get it down to 15%. Okay, and you want to write a sentence answer like that. So again, another one where you had to multiply your final amount, the 4 kilograms, by 15%. But you didn't have to multiply your final amount by anything here, because the $109.50 was a total cost, not a cost per pound. Okay, so that's your difference. Okay. All right, again, try forward, stop the video, and then fire it back up to see if you're right. Okay, so it says how many pounds of each should be combined? Each what? Well, peanuts and M&Ms. So X can be the pounds of peanuts. Y can be the pounds of M&Ms. And if I add those two amounts together, that has to equal 12. And so the next part is how much each amount costs per pound. Right? The peanuts are $4 per pound. So I got to take 4 times the number of pounds to find out the total cost of that. M&Ms are $3.75 per pound. So I got to take $3.75 times Y to find out the total cost there. But the 12-pound mixture already has a total cost of 46. It's not 46 is not a price per pound, so we don't have to multiply that by anything. Okay, so those are your two equations. I would multiply the first equation by what, maybe negative 4. I'm going to use elimination again because it just sets up to be easier. And so we get negative 0.25y equals negative 2. Divide negative 0.25 to both sides, and you should get 8. So that means that we're going to use 8 pounds of M&Ms and apparently 4 pounds of peanuts to get our new mixture. Okay? Hopefully this makes sense. Again, get into the homework. Writing is trying. And if you're not getting the equations, try to figure out why and learn from that. And if you can't, come in and see me and we'll figure it out. Homework sitting out on Canvas. Go get it done.